Hello, stats friends. Well, don't I just feel like the biggest dum-dum in the world? I was so excited when I was finishing up chapter 5 because I was like, this is the end of semester 1. Nope, no, it's not, because there's a whole nother part of that unit that I forgot. So chapter 6 is actually the same part of the unit as far as the AP outline looks, and we have to continue our work with probability as we look at random variables and probability distributions. So don't celebrate too far here, guys. We're not quite done with semester 1. So today we're going to discuss section 6.1, discrete and continuous random variables, which we do have a little bit of knowledge about what those vocabulary terms mean, but now we're going to see them in distributions, specifically probability distributions. So a lot of learning targets today. This lesson should be broken up into 2 days. It's kind of the halfway point, and hopefully I am aware of enough of my surroundings to tell you where that halfway point is. All right. So first, let's talk about a probability model. So it describes the possible outcomes of a chance process and the likelihood that those outcomes will occur. So consider tossing a fair coin 3 times. Define the random variable x as the number of heads obtained. So if you think about what could happen with your 3 coins, one outcome is it would land tails, tails, tails. So that would be getting 0 heads, and that happened in one of the outcomes of the sample space. And then they kind of displayed everything beyond that. So what does it look like when you land on heads once and twice and 3 times? And then you'll notice there are 8 different outcomes here in the sample space. So all these probabilities are, something over 8, something over 8, something over 8. So this is a good display of a probability distribution in a table. So the random variable takes numerical values that describe the outcomes of a chance process. The probability distribution of a random variable gives the possible values and their probabilities. So as we're just kind of looking at this data, which events are more likely when you're tossing 3 coins? Well, it's more likely, according to the probabilities, that you would get either 1 heads or 2 heads. Of course, we know what that means. It doesn't mean it's not going to happen. It's just more likely that it would land on 1 heads or 2 heads. So probability distribution for a discrete random variable. So now we're going to kind of differentiate between discrete and continuous. The example that we just saw there with the flipping of the coin, that was a discrete random variable. Let's see, we already covered that part. So for the probability distribution to be valid, there's a couple things it must satisfy. 2 requirements. So every probability is between 0 and 1, and it could be 0 or 1 in some of them. Well, 1's kind of a all or nothing thing, but whatever. And then the sum of the probabilities has to add up to 1, because this table should represent the entire sample space. So we're going to see a problem in a moment where there's like a missing probability and we got to figure it out. We got that. So let's think back to something we did in chapter 1. We used to analyze distributions of quantitative data, and we discussed their shape, center, and variability. We also discussed outliers, but we're going to kind of ignore that for today. There shouldn't be, strange outliers in a probability distribution, because it's, everything that's happening by chance. And not that chance is perfect, but, it's theoretical probability. In that example, we just saw the coin toss. We'll do the same with probability distributions of random variables, but for now, let's talk about discrete. Oh, no, Abruzzo, that's not at all what you're supposed to say. We're about to do this with probability of distributions of random variables. Here we go. So we're going to describe the shape, center, and variability. So this particular one is referring to an example in your textbook about the probability of newborn babies getting a certain APGAR score. So I forget what APGAR stands for, but basically it's the test they give newborns to see how healthy they are after they're born. I would like to think that my kids were, very above average, but after doing these problems, I realize that they're probably just average. But that's okay, they're really good kids. All right, so the highest APGAR score here is out of 10. And then their question here is about describing this distribution. So can you tell that it's skewed to the left? I hope so. It is single peaked at 9. And we're not really ready to discuss variability yet. We have to do a little bit of calculation for that. So then there's a follow-up question. And it says we can interpret our earlier result. So I think they're kind of skipping some things that are in the textbook. So in theory, I should have gone back and grabbed some snips of the textbook. But where it says probability of x being greater than 7 equals 0.809. What that's saying is, so greater than 7 doesn't mean we count 7, but we would count all the kids who, or the probabilities that they would score an 8 or a 9 or a 10, and we'd add them up. Now in the book, I think there's like a table where we would add up those three results, and it comes out to 0.809. So that means 81% of all newborn babies have APGAR scores greater than 7. And we'll stress this in a moment, but when we go to apply these findings in our probability distribution, they're only true if we apply them to like a vast number of, a sample or possibly the whole population. All right, let's talk about this next part. We got Pete's Jeep Tours offers a popular day trip in a tourist area. There must be at least 2 passengers for the trip to run, and the vehicle will hold up to 6 passengers. Pete charges $150 per passenger. Let C equal the total amount of money that Pete collects on a randomly selected trip. So the probability distribution is given here. Remember, he has to have at least 2 passengers, so you'll notice the lowest amount here that he would collect is $300, and the most he can have is 6 people, so that's where that $900 is coming from. And these are the probabilities that are associated with each of those dollar amounts. So the first challenge they have for us is to make a histogram of the probability distribution. Now, this histogram is, well, first of all, again, it looks like I drew it, but somebody else did. Um, you'll notice the bars aren't done in like a range per se, but the middle, so like these are the markers for those discrete random variables. So 300 bar and the 450 bar and the 600 bar and so on and so on. Now the height of the histogram bars are going up to their associated probabilities. So this one is in between 0.1 and 0.2, so that's where it's at 0.15 from the chart over here, and then so on and so on and so on and so on. So we have our histogram drawn for us. That was nice. Now let's describe its shape. So are you noticing that this is roughly symmetric and has a single peak at $600? I hope you noticed that. All right, let's check our understanding. So this next one, they have Indiana University Bloomington is going to post the grade distributions for the course online. Suppose we choose a student at random from a recent semester of this university's business statistics course. The student's grade on a 4-point scale, where A is a 4 and B is a 3 and C is a 2, and so on and so on. We won't talk about the others. Is a random variable X with this probability distribution. So they want you to answer 3 questions. Write an event. The student got a C using probability notation, and then find the answer to that. So you notice they're missing here the probability of a C. And then they want you to explain in words what the probability of x greater than or equal to 3 means, and then what is that probability? And then they want you to make a histogram of the probability distribution. So pause the video. Oh, describe its shape too. Pause the video and let's see what you can do. All right, answers. So that first one says probability notation that a student got a C is going to be written like this. The probability that x equals 2. So remember, we're not looking for inequality here because they wanted exactly a C. They didn't say something like at least a C. So that's why you're seeing probability of x equals 2. And then to find that, well, basically we know that these should add up to 100%. So if we were to subtract all of these known probabilities away from a 1, that's where this number of 0.138 is coming from. So then the next question says, interpret what this means. So the probability of x is greater than or equal to 3. That represents the probability that a student got either an A or a B, because greater than or equal to 3 for our distribution would be a 3 or a 4, which represents an A or a B. So to find that, we just have to add those two together. So I would go back to the table here and I would just add those two together, which is what they did, 0.819. And then they drew the histogram for you using technology, and it's a real beauty. But you'll notice in the middle of each bar are those discrete variables. So a 0, a 1, a 2, a 3, a 4. And then the height of the bar is going up to its subsequent probability. And again, those came straight off the table with the exception of the one that we had defined. All right. So how do you measure center, which is we know as the mean, but it's actually called an expected value in probability distributions of a discrete random variable. So the mean, known as the expected value of any discrete random variable, is an average of the possible outcomes, but it's a weighted average. So each outcome is weighted by its own probability. There's some really cool examples that hopefully I'm gonna have time to do in class with you where, like raffle tickets and lottery and like, what is this lottery ticket's value? We know we're not likely to win the lottery. So what really is it worth? Of course, we all hope we win, but eh. All right, so the mean expected value of a discrete random variable is the average value over many, many, many repetitions of that chance process. And that's the key to these problems that I think sometimes it's hard for us to remember. Whenever we reference the context of the question, it's always in reference to many, many, many trials or many, many, many things. You can't just say, this is what's going to happen on the next thing. Nope, it's got to be many, many, many. So the notation is a little kooky. What they're doing is they're taking the value and they're multiplying it by their corresponding probabilities, and they're just adding each of those values together. So value times probability plus value times his probability, and so on and so on and so on. And this use of ellipses is actually okay for the AP exam because they obviously don't want you writing forever and ever. That's not the point. So if you have like a whole bunch of values, a beginning and ending, and you want to do like this times this plus dot dot dot, and then do the last one, that'll be really a great time saver for you. This is the fancier notation from your book. Remember, this is a summation, so it means to add them all up for every single x and p value that correspond with each other. That's that sub I thing they're referring to, every single one. The summation notation is weird. Now, I will warn you on your AP formula sheet, the notation does look a little bit different, I think. We'll have to look closer at that in class. Notice, however, they do call this the expected value. They use the symbol mu because it is a mean. So it's the mean of our discrete random variable distribution. Boop, right there. Have you noticed they've been using capital X? I always thought that was curious, just weird thoughts from Abruzzo. I'm sure they have their reasons. All right, so let's figure out the expected value for this question. Now they've notated where it is. They say, recall it's the balance point of a distribution. I actually don't want us to calculate it for this one. Okay, sorry. Let's just interpret it this time. So how do we interpret that 562.5? Now here's the key. If we randomly select many, many Jeep tours, Pete will make about 562.5 per trip on average. Okay. So we're not saying the next time he goes, that's going to be his average. We're saying if we randomly select many, 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 and then find the average, that's what we would expect him to make. So he can't just give one Jeep tour tomorrow and be like, boom, I got my money, let's go. I mean, he could, but we can't expect it to be the true value of 562.5. All right, back to those babies. So earlier we talked about the APGAR scores for the newborns, and there's the table with probabilities that I was looking for earlier. Thank you. So the next question is find and interpret the expected value of x. So they're looking for mu sub x. Oops, spoiler alert, there it is. So they took each value and multiplied it by their own probability for each value. So 0 times this, 1 times this, 2 times this, 3 times this, and then they added them together, and notice how they did the dot 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 thing. Because mathematicians are too lazy and statisticians are even lazier. We don't want to write all that out. So the expected value here is 8.128. So what does that mean? If many, many, many newborns were randomly selected, their average APGAR score would come out to about 8.128. Pretty sure my kids scored somewhere in the eights, so I guess I feel a little less special. They weren't miracle babies, I guess. Sorry, kids. They're pretty awesome though, like I said. All right, well, what about median? So if you want the median of a discrete random variable, well, remember, median is the middle. So middle is going to be, once we hit the 50th percentile. of the probability distribution. So their suggestion is, what if you created a cumulative probability distribution where you start adding them up as you go along? So here, I really don't know what this data is from, but that's okay. So we have our probability and our total, that's fine. But notice this is just the probabilities individually. But if you look at the bottom row, you have the cumulative probabilities. So 0.15 plus the 0.25 is how they got the 0.4. And then when you add the next 0.35, that's how they got the 0.75, and so on, all the way up to 1. So if you're looking for the 50th percentile, well, I mean, technically it falls in between here, but remember we have discrete variables here. So it is at or above the first time you would have hit 50th percentile. So we're going to have to go with this guy here. So the median would be the 600. Okay, because remember, this is not continuous. We don't have numbers in between 450 and 600. It's just one or the other. So 450 wasn't big enough. It wasn't at 50th percentile yet. 600 met the mark. All right. So mean is our measure of center for any discrete random variable. It shouldn't surprise you that now we're going to use standard deviation for variability because they kind of go hand in hand, don't they? You talk about mean, you know the next thing is going to be standard deviation. So standard deviation, remember before you get to standard deviation, you can find what's called variance. Variance is figuring out how, well, it's a little confusing, but it's the squares of the differences of the values from the expected mean. So look at, man, this hurts my eyes and I'm the math teacher, right? So they take the x value, they subtract off the expected value, and then they square it to make it positive. And then they multiply it by the probability for that particular x value. So we're going to see an example in a minute, but the value is going to be this, and then I expect it to be something else. I'm going to find the difference, square it, and then multiply it by the probability. And we're going to do that for each one of these. And then we're going to add them up. So this summation notation is the quote shorthand of what we're doing there. And then remember, guys, this is just the variance. The variance is the standard deviation squared. So to find the standard deviation, you got to come back and you got to square root that whole mess. So it's the sum of the square roots of all of that business. Remember, the reason we have to square root on the variance to get standard deviation is because your units are wrong. You're measuring points squared and you need just points, so you got to square root it. All right, let's calculate and then interpret the standard deviation of that baby problem. So remember, we found the expected value of 8.128. So our next job is to do the difference, right? So the value minus the expected, and then we're going to square it, and then we're going to multiply it by the probability. And we're going to do that for each one of these. Now, do I want to do this by hand? No, no, no. Am I going to do it by hand? Only if I have to. And sometimes I'm real lazy, guys. I might write out what I'm supposed to do by hand and then actually go do it on my calculator, and we'll show you later how we can do that. But there might be times in the AP exam where they say, like show how to do the, and right here they have variance. They haven't square rooted yet, but show how to find the standard deviation, how to calculate the standard deviation, or it could be like a multiple choice question where they're like, which of the following is? So we do have to kind of be ready for anything. We know that. So we've calculated the standard deviation to be 1.437. How do we interpret that? So don't forget this many, many, many thing, right? If a randomly selected newborn baby's APGAR score will typically vary from the mean, which they noted here of 8.128, by about 1.437. Now, they didn't specifically say the quote many, many stuff. I'm not sure why they didn't in that question, but yeah. All right, so doing it by hand, not fun. I think we can all agree with that. So what if we did that same question and we used our calculator? So what we would do for a discrete random variables question, if we wanted to calculate the mean and standard deviation, or expected value, which is the mean, of course, is we could put the x values into list 1 and their corresponding probabilities into list 2. And then what's kind of cool is we use list 1 as the x list for, well, here it's a histogram, but the frequency list is for list 2. So remember, list 2 is all the probabilities. So it's going to naturally tell you, like, quote, how often that shows up through the probability. So if you wanted to look at the distribution, you could just plot a histogram. Now they manually adjusted their window. I have a feeling if you just did zoom stat, you'd get a pretty decent window, but the bars might be a little messed up. They might not be counting appropriately for what the problem was. But at least you would be able to tell the skewedness. That might be nice. Anywho, what if I wanted to calculate the expected value or the mean and the standard deviation? Well, same thing, but this time we're going to go to one variable stats and we're going to put in L1 for the values and then L2 for the frequencies. So again, it's gonna what really is happening in the calculator is it's multiplying the L1 by the frequency list. So that's cool. I remember back in my day, we used to just create a third list where we multiplied L1 times L2, and then we did one variable stats on that. You sure could. That would work the same way. And then you would just leave the frequency list blank. Trying to read this message down here. Okay. It's warning you about the frequency list and being careful about your notation after that. Yeah. All right, so it says the calculator's notation for the mean of the random variable x is incorrect. So they use x bar. For these particular problems, it is not x bar, it is mu sub x. And then the standard deviation actually is correct. There we go. Nice. All right, exam tip. If you're asked to calculate the mean or standard deviation of a discrete random variable in a free response question, you must show the numerical values substituted into the appropriate formula. As in the previous two examples, feel free to use those ellipses, so dot, 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 so you don't have to write them all out. You may then use a method described in the technology corner to perform the calculations with one variable stat. Writing only one variable stat, L1, L2, and then saying here's the values is not going to get you credit. Also, be sure to avoid incorrect notation so that's really key. Sometimes kids will just use the x bar because that's what the calculator says. No, it's mu sub x, so watch your notation. Check our understanding. So we have some data here. Oh, same data with those grade distributions. This time they want you to find the mean or the expected value and then interpret it, and then find the standard deviation and interpret that. So you should pause the video and give this a chance. You might also want to take the time to try to write out your calculation on your paper, just so you know you can do this for the AP exam and your homework and your quizzes and the test. All right, answers are coming next. So the expected value, mu sub x, would be each of the probabilities times their x values, and then we added them all up. And this time they went ahead and wrote them out because there's only 5 of them. And then it came out to 3.222. I hope you got that. So to interpret that, remember this is the many, many, many part. If many, many students are randomly selected, their average grade will be about 3.222. Don't you just love stats? Like, about, if this happens, in the location of, nothing's ever like said so severely that it's the absolute truth, but that's life. All right, so here they showed the standard deviation calculation, but they started with the variance. Me personally, I don't necessarily start with the variance unless I have to, so I will say like sigma sub x, and then I'll put a square root over all this mess. There's nothing wrong with doing that, but they do want to see kind of your steps if you're forced to show this by hand. So remember what they did to find this, in this case, the variance. They did x value minus the expected value squared times his probability for that particular x value. And then they did it for all the other ones, and they added them together, and then they square rooted that number, and they got, boom, that. Now, did you actually calculate that in your calculator that way, or did you use your one variable stat? It doesn't matter. It's going to be the same, or at least similar, depending on how you rounded and truncated. There is, I don't know if it's in this note or not, you got to watch your rounding. So your expected value, you don't want to round like too far. So a lot of kids see that and they go 3.2. That's not going to be a really good measure because remember, we're going to apply that number to many, 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 many of them. So we want to keep a lot of significant digits on it. And I don't necessarily know that there's a rule, like you have to follow the sig figs, but don't round too much. So the interpretation for that standard deviation is if many, many students are randomly selected, their grades will typically vary by about 0.879 points from the mean of 3.222 points. So notice the context there, notice the vague language, and of course the reference to the if many, many are selected. I love that. I feel like we should get a button. If many, many. That could be our new class motto, guys. All right, this is probably, well, if we haven't already hit it, this is most definitely the day 2 of the lesson. It might have already happened though, and I wasn't real good at telling you. We have continuous random variables now. So we've been working with discrete, but now let's talk about continuous. So continuous random variables can take any value on the interval. So they're not those counting numbers anymore. Now you can get numbers in between. So we learned about continuous and discrete before. The probability of an event involving a continuous random variable is the area under the density curve and directly above the values on the horizontal axis. So my friends out in calculus, you guys know you do a lot of this in calculus if you've already had part of calculus. Finding area under the curve is a huge portion of calculus. Well, sometimes we have a probability distribution for a continuous variable that looks like this. Now, my third grader could find the area of this density curve, kind of. I mean, maybe with a little help from mom. It's a rectangle, right? So this problem, I don't really know the context of this problem, but it's having your y values here represent the randomly generated number, uh, and it goes from 3 to 7, and then you have a height here of 1/9. So to find the area under this curve, well, you would just multiply. That's a distance of 4. Abruzzo, you can count, right? That's 4 times 1/9, and that would be the area, meaning that's the probability that your y value is between 3 and 7 inclusive. 4, what did I say? 4 times 1/9. So 4/9. Again, I have no context, so I don't really know what that problem was about. All right. Miss Selena here works at a bookstore in the Denver International Airport. She takes the airport train from the main terminal to get to work each day. The airport just opened a new walkway that would allow Selena to get from the main terminal to the bookstore in 4 minutes. She wonders if it would be faster to walk or to take the train to work. So let y equal Selena's journey time to work in minutes by train on a randomly selected day. The probability distribution of y can be modeled by a uniform, that's the rectangular one, density curve on the interval from 2 to 5 minutes. Find the probability that it will be quicker for Selena to take the train than to walk. All right. Well, turns out, so 2 to the whole thing, the whole axis here is 2 to 5 minutes, but it's only going from 2 to 4 minutes. Okay, 2 to 4 minutes. So the distance here, 2 to 4 units, that would be 2. And then the height of your curve is 1/3. So we would multiply those together and we'd get 2/3. So the probability, 2/3 by the way, we know is 66.7% when we round. So the probability that it will be quicker for Selena to take the train than to walk, well, the reason we stopped this at 4 is because this before 4 is going to be the probability that it was quicker than the train, right? That was the whole question, quicker than the train. So there's a 66.7% chance that it will be quicker for Selena to take the train on a randomly selected day. Okay. I don't know how Selena feels about that. Maybe she hates the train. Maybe there's a bunch of like creepy dudes on the train. My sister lives in Chicago. She tells me all about these things. This is an airport in Denver, not quite the same thing. All right. Continuous random variables still. This time we have what we know as like the normal curve, looking like one of those normal curve questions. So we have a normal distribution with mean of 64 inches and a standard deviation of 2.7 inches. Suppose we choose a young woman at random, and let y represent her height in inches. Find the probability that her height is between 68 and 70. Notice the inclusive because of the equal to bars under there. So what we're going to do now is we're going to show how we can find that area first using our z-table and z-scores. And then we're going to come back and do it with calculators. And we're going to do it like the super lazy way and also like the halfway lazy way. So first, let's find z-scores. So remember, your z-score is your x value, so 68, minus your mean, which is 64, divided by your standard deviation of 2.7. So that first guy has a z-score of 1.48. And then similarly, we're going to find his z-score by doing 70 minus 64 over 2.7 and got 2.22. Now, remember, if we're relying on our table, the next thing we have to do is go to our table A, and then we read the table and remember that it measures down the curve. So when I look up a z-score of 1.48, that's measuring this away, right? And that comes out to 0.9868. So I'd kind of jot that down. And then this guy, if I look up a z-score of 2.22, he measures all the way down this way. And that's nope, I did that backwards. This was 0.9306. This was 0.9868. And the area that I wanted was where those two overlapped. So we subtract those two values. And we get an area of 0.0562. Now, you know I hate the table, guys. Unless I am absolutely forced to use the table, I'm not going to. I would use my technology, and I'll be honest, I wouldn't do this either. Now please note how they used the technology and how they displayed it to their reader. They didn't just say normal CDF and then listed off values. They indicated what was what. So their lower bound was 1.48 z-score, their upper bound was 2.22, a mean of 0, and a standard deviation of 1. That tells my reader that I standardized my scores, and they got actually they got the same area. This is the Abruzzo method. I wouldn't have even bothered to find z-scores because I'm very lazy. So I would have done normal CDF using the data, 68 to 70. So lower bound 68, upper bound 70. And I would have just used the mean and the standard deviation given to me. But the key is that I told my reader what I did. So this is most definitely what I would have done. And that's just because I'm lazy. No other reason. It's not better. I'm just lazy. So to interpret that, the probability that a randomly selected young woman has a height between 68 and 70 inches is about, 5.6%, 0.056. Fascinating, isn't it? So this is warning you about don't just write down calculator speak. So if you wrote down normal CDF, blah, that's too lazy. That's beyond Abruzzo, okay? That won't get you your points. You want to make sure that that communication is clear to get your full credit. So you would have to specify lower bound, upper bound, mean, and standard deviation. They will let you abbreviate standard deviation. They're nice like that. Oh my gosh, we're done? Time flies. Okay, I super lied about day one, day two. I don't know. I'll be honest, I don't know where I separated day one and day two anymore. I hope you didn't have to watch that whole lesson for no reason, some of you out there. All right. I appreciate all of you. Good. Have a good time.